So now we know how to recover the three-dimensional structure of a scene using depth from focus. You have a plane of focus and you're going to simply sweep this plane of focus through the three-dimensional scene. Take a stack of images, that's called the focal stack. Using that stack, you can figure out when each point in the scene came into focus, and that information can be used to compute the depth of the point in the scene. So it works well, it's been widely used. The only downside is that it does require a relatively large number of images, typically between 10 and 20 images. If you're looking at a real-time application, that may be too many images to capture for each depth map, and we would like to do something like depth from focus with a much smaller number of images, and that is depth from defocus. So depth from defocus is based on the observation that if we can estimate not when a scene point comes into focus, but how much a scene point is blurred, then that PSF for that particular point and the size of the PSF is all the information you need to estimate the depth of the corresponding point in the scene. So let's take a look at what we mean by that. Here is a single image shown to you, and obviously the camera has a depth of field and points in the scene are differently blurred from each other. And if you look at three different patches here, say this one, which is on this measuring tape, you see that it has this PSF associated with it. And this point, which is further away in the back, has a much bigger PSF. And this patch on the printed sheet of paper has this smaller PSF. So somehow if we can estimate the PSF corresponding to each point in the scene, then that's all we need. That PSF tells you what the diameter of the blur circle is, that's B. Once you have that, then you can estimate the depth of the point in the scene. And that is what depth from defocus seeks to do. It's going to try and measure the amount of defocus at each point. So let's take a look at how it works. So we know how defocus works. Here is a point, and here is its blur circle in this image. And we know that B divided by D, B divided by the diameter of the aperture, is I minus S divided by I, where I is the image plane location where the point is focused, and S is the distance of the sensor from the lens. And so from this we can estimate, if we know what the blur circle diameter is, we can estimate I. And once we estimate I, that is, in other words, we're actually estimating from the blur circle diameter where the point would have been focused, and from I we can estimate O. So in other words, if we're somehow able to measure the diameter of the blur circle, then that's all we need to estimate the depth of the point in the scene. That's O right there. The question is, how do we do this? So let's take a look at whether we can do this with one image, and you probably know the answer already. Here is your image. This is the focused image of an object, and we know that that focused image convolved with some PSF, unknown PSF, is going to give you the blurred image that you capture. When I say unknown PSF, we don't know what the width of the PSF is. That's what we're looking for, the degree of defocus. So what's known to us here? Well, it turns out in this case, the only thing that's given to us is the image, the output image right here, the captured image. We don't know what the focused image looks like, and we don't know what the PSF is. So you have one equation essentially, this convolved with this is equal to this, that's your equation, one equation, and you have two unknowns, both F, the image, focused image, and H, the PSF. So then what if we had two measurements or two images? So let's say you have a camera, and for some setting of the camera you capture one image, and then you change the focus setting and you capture another image. So now you have the same focused image convolved with your first PSF with some width sigma 1, gives you this image G1. That's one of your captured images. And then the same focused image convolved with the second PSF gives you this captured image, which is even more blurred. And we, of course, have these two, and we don't know F, the focused image, obviously. We've never seen this object in focus. And we also don't know the two PSFs, the two widths of the PSF. We know the model of the PSF, but we don't know what the width sigma 1 is or the width sigma 2. So what do you have now? Well, you have two equations, but you have three unknowns. The three unknowns being F, sigma 1, and sigma 2. So it seems like every image that you capture, you're going to be short by one equation. The number of unknowns is going to be one greater than the number of equations. Well, there's hope, and that's because we are controlling the imaging system, the things we know about it. What do we know? Let's say that in this particular case, you're not actually changing the sensor position, but instead you're actually changing the diameter of your aperture. There are many ways to do this, but let's say that you're actually changing the diameter of your aperture. So in that case, the diameter of your aperture in the first case is D1, and that produces a PSF sigma 1, and we don't know what sigma 1 is. But when you use the second diameter, D2, you get a PSF sigma 2. Again, we don't know what sigma 2 is, because sigma 1 and sigma 2 depend on the depth of the corresponding point in the scene. So if you look at the blur circles, you have blur circle B1 is D1 times 1 minus S divided by I. S is being held constant here, the sensor location, because we're changing the diameter of the aperture. And then you get B2 in this case equal to D2 times the same factor right here. And if you look at the relationship between sigma and B, we made this approximation earlier that sigma is roughly equal to B divided by 2. And so sigma 1 is equal to B1 divided by 2, sigma 2 is equal to B2 divided by 2. So now you see that sigma 1 by sigma 2 is equal to D1 by D2. So we don't know what sigma 1 and sigma 2 are, but by changing the aperture and knowing the ratio of the two apertures that you use to capture the two images, it doesn't matter which point we're talking about in the image and what the depth of the point is, we know that the ratio of the widths of the two PSFs for that point are going to be equal to the ratio of the diameters of the two apertures. Sigma 1 by sigma 2 is equal to D1 by D2. That applies to all points in the scene, irrespective of their depth. So now let's take a look at whether we've made any progress. So we are now looking at the case where we have taken two images. So what are our unknowns? We don't know the focused image. We don't know the first PSF and sigma 1, and we don't know sigma 2. But we have three equations now. Equation 1 is the captured image G1 is F convolved with H sigma 1. And the captured image G2 is F convolved with H sigma 2. Those are two equations. And of course, these two equations have three unknowns, which we saw before, F, sigma 1, and sigma 2. But we also have this additional constraint now, which is sigma 1 divided by sigma 2 is equal to D1 divided by D2. And it's convenient to look at these three equations in frequency domain or Fourier domain. If you find the Fourier transform, take the Fourier transforms of these two equations, you get this. We know that convolution in spatial domain is equivalent to multiplication in Fourier domain. So you have G1 UV is equal to F UV times H sigma 1 UV. And the same with the second image. And this constraint remains the same. So now what we're going to do is simply take the ratio of G1 to G2 right here in these two equations. So when you do that, you get this expression right here, and an interesting thing happens. Essentially, F UV gets cancelled out. And what is FUV? That is the Fourier transform of the focused image fxy. So in other words, what's removed from this equation by taking this ratio is the content of the scene. The texture and the frequencies in the scene are essentially removed. And you get the ratio of the Fourier transform of the first PSF and the second PSF. And we know that the PSF itself, we modeled it as a Gaussian. And so the Fourier transform for Gaussian is a Gaussian. So essentially, that's what you get here. G1 by G2 is the ratio of two Gaussians in U and V with sigma 1 and sigma 2. So now we can take the natural log on both sides, and we get sigma 1 squared minus sigma 2 squared equal to this, and everything on the right-hand side is known. But yet, we have two unknowns here, sigma 1 and sigma 2, and that's where our third constraint comes in, which is sigma 1 divided by sigma 2 equal to d1 divided by d2. This is known. So here you have two equations in sigma 1 and sigma 2, and we can solve for sigma 1 and sigma 2. In fact, you can solve it using any one frequency, uv. And as long as the values of G1 and G2 are non-zero for that particular frequency, you can solve it using just one frequency. And so we can solve for sigma 1 and sigma 2. And once we've done that, we can take any one of those, and that gives us the corresponding diameter of the blur circle. We can use that to find the depth of the corresponding scene point. Now the problem here is that in using G1 and G2, we really have to use the high frequency values in G1 and G2. And that's because those are the values that are most impacted by defocus. We know that defocus is a low pass filter, so we really need to focus on what's happening to the high frequencies. In doing so, we have to face the fact that high frequencies is exactly where the noise resides in the image. And so that makes this approach somewhat sensitive to noise. So let's take a look at an even more direct approach to solving the problem. And this is called reconstruction-based depth from defocus. So once again, here are the three things we are looking for: sigma 1, sigma 2, and the focused image f. We want to find these so as to minimize what we'll call the reconstruction error. What is a reconstruction error? Let's pretend for a minute that we have the focused image and that we have sigma 1. If we have sigma 1, we have the PSF corresponding to sigma 1. So the focused image convolved with that PSF should be exactly equal to the first captured image G1. That is, if your reconstruction is right. Similarly, the focused image that you've reconstructed convolved with H sigma 2 should be exactly equal to G2 if your reconstruction is perfect. So this term corresponds to the error in the reconstruction corresponding to G1. This one corresponds to the error with respect to G2. You take those two errors, you square them, add them up, and that's what we're going to define as a reconstruction error E. And now what we want to do is find sigma 1, sigma 2, and f that minimize this error. Now remember, we have one additional constraint, which is sigma 2 by sigma 1 is equal to d2 by d1. So we can use that in this reconstruction error so that we are down now to just two unknowns, f and sigma 1. And we want to find the f and sigma 1 that minimize E, and we know how to do that. We essentially find the derivative of E with respect to sigma 1, set it equal to 0. Derivative of E with respect to f, set it equal to 0. And so that's an optimization problem. And then we can compute sigma 1. And from sigma 1, we know that B1 is 2 times sigma 1. We know that. We plug that into our expression for object distance, which we discussed earlier, and you get the depth of the point in the scene. So what we've seen now is a way of recovering the three-dimensional structure of a scene from just two images taken under different focus settings. And rather than finding an image where a point is best focused, in this case, we're looking at the relative blur of each point in the two images and then figuring out what the depth of the point is. So talking about focus settings, there's two different ways to implement this. One is, of course, by changing the aperture, as we discussed earlier. When you change the aperture, you're going to change the defocus of each point in the scene in the two images. And the other method is, of course, by changing the position of the image sensor. And that's this approach right here. So now let's take a look at a couple of example results. In this case, we are actually looking at two images captured by moving the sensor location. This is what we call a near-focused image. You can see that this patch right here is in focus, whereas everything that's farther away from the camera is out of focus. And in this case, you have a far-focused image where you see that this area is focused and things that are closer are actually out of focus. And from these two images, we are able to get this 3D reconstruction of the scene. And now I want to show you one of the early depth from defocus systems that was developed to be real-time. So in this case, you have your scene sitting out here, and you have a lens here, imaging optics, the lens right here. And this lens creates, of course, an image. And this image is actually split into two images using what's called a beam splitter. Essentially passes half the image, half the light through, and the other half is reflected. So you essentially get two identical copies of the same image, but one image is being captured with a sensor which is located here, and the other one with a sensor that's located here. But these two sensors are, in terms of path length, they're actually displaced slightly. So essentially what you're doing is capturing two images of the same scene using the same lens simultaneously, which correspond to two different sensor locations. So that allows you to do depth from defocus. But since the system was being developed for surfaces that are arbitrary in terms of texture, one also had to be able to accommodate objects that did not have any texture. And this is something we discussed earlier. If this is your object and this is the surface you want to reconstruct, depth from focus or defocus is not going to work because there is no texture on the object. So the idea here was to actually force a texture on the object by using this light source right here. So there is a light source where the light goes through an optical filter that produces a very fine illumination pattern onto the scene. And therefore, one is actually, through the illumination, forcing a texture on the scene. And at that point, the scene takes on that texture as its own, and then depth from defocus is being used to reconstruct the three-dimensional structure. It works very accurately because now you have a very strong texture at all points in the scene. So here is an example of how this works. It's a human hand right here. And what you're seeing on the display right here is the depth map being computed in real time. The closer the point is, the brighter it is. So you can see that you get a very nice reconstruction of the hand as it moves around. And this was perhaps the first real-time demonstration of depth from defocus, where the three-dimensional structure was being computed at roughly 30 frames per second. Here's another example. It's a cup, and there's some milk in the cup. And you can, in fact, see that the cup is reconstructed, and so is the liquid that's flowing out of the cup.